I tutored someone from the class, and she said that, yeah, the professor doesn't know how to change the volume.
Oh, sorry, what?
The professor doesn't know how to change the volume.
In the class next to
Oh.
I was like, oh wait, are you right next? What time is your class? And I was like, yeah, that class is loud. And she was like, yeah, she doesn't know how to change it.
Okay. Yeah, same. It must be really bad for them. So Marvin noise is not intruding in here, so I'm not sure what's going on. Maybe we're taking a quiz or something.
I mean, if someone was sleepy, they're not as sleepy anymore when they get to that class.
So that's a teaching tactic. Okay. Okay.
It doesn't work for me, sorry.
So my goal today is to hopefully get through the rest of this part so that on Tuesday, actually jumping into numerical methods, since that's what the class is supposed to be about. Where I was before was getting into the heat equation. Okay, so what we have is Ut is velocity of u, so the heat equation in its simplest form. And this is for a free space. So the spatial domain is all of Rn. Okay, so this is okay. And then we have initial conditions. Okay, and we have the solution that's just a convolution in the spatial variable. All right, so I could also write this as phi convolution with u naught expressed as a function of x and t. Okay. Now, and phi is the fundamental solution. And I wrote the formula for that last time. It's a decaying exponential. Okay. Now, let's see. I'm sure things in a different order than the notes, but okay. Now, suppose I change a problem just a little bit. So I should mention it's out of order from what's currently in the notes, so I may rearrange the notes before I post them to Canvas. So the inhomogeneous Ibvp initial value problem. Okay. Well, I guess you don't really need to watch 5 minutes of video because everything I've done is on the board now. So here we have ut is the Laplacian of u, and then a plus a source term f. That's some function of x and t. Okay. And then I'll assume that the initial data is 0 this time. Okay. So it turns out it's actually pretty easy to write down the solution of this problem as well, and related to the solution of the homogeneous PDE here. So the solution is u of xt is an integral from 0 to t, and then what's inside the integral bears a close resemblance to what we see here. So it's the integral over Rn, and fundamental solution of x minus y. But instead of t, we have t minus s, and then the source term evaluated at time s. Okay, and then we have dy for the integral over the spatial domain, just like here, and then ds for the integral over time. All right. Now, what I can do, though, is I can write this as the integral from 0 to t and express this integral, because think that this integral looks so much like this that I want to take advantage of that to simplify how this solution is expressed. So for my integrand, I'm going to put u of, actually, I'll use a different letter. V of x, let me try to get my notation right. This might be written later in my notes. Okay. Okay. All right, so in this case, we have solution expressed at time t minus s. I'm going to add an additional parameter here that I'll just refer to as s. Now I'll explain all this in a second. Okay. Where each one of these v's, v is a solution of a homogeneous heat equation. So I need to make sure my v's and u's are nice and distinct. And it's still a free space problem. And here t is greater than s. And the initial data and is actually specified not at time 0, but at time s. And it's equal to f at time s. So, so let me explain in words what's happening here. That you can think of f as, because it's a source term, it's like an external heat source. So at each instant s, f of ys is treated like initial data. That initial data is evolved from time s up to time t. That's why the gap in time here is t minus s. We start at time s, evolve up to time t. So over that span of time, t minus s. But that's true for each s between 0 and t. So whatever the source term is doing at each instant in time is evolved up to time t, and then the effects from all those times in between, from 0 to t, are added together. Really, they're integrated, but that's you think of it as adding. So that's called superposition. Superposition comes up a lot in PDEs. That so the solution u of xt is a superposition of solutions of these homogeneous initial value problems. So we're taking the solution of initial data starting at time s, and we're evolving it this far in time. Okay. Now, actually, I should be more careful with my notation here. Okay. Since I'm starting at time s, here I should just have t. So it's starting from s, ending at t, so the time span is still t minus s. Okay. All right. Okay. Now, this is called Duhamel's principle.
The whole solution, correct?
Yeah, in other words, how the solution formula is arrived at is using Duhamel's principle. Duhamel's principle is a way to describe the solution of a non-homogeneous PDE in terms of solutions to a related homogeneous PDE, since those are so much easier to solve. And this integral that's used to combine all of these solutions, because you could think of this as being a solution. Is this a solution of a homogeneous problem for each individual s, each instant s? And by integrating, you're adding them all together. That's an example of what we call superposition. So the integral over t, from 0 to t, accomplishes that combination of all these solutions. All right. So for each s, source term is treated like initial data, evolved from time s to time t, and that's thrown in the mix. We take them all. That's our non-homogeneous solution. So then, now notice here, this problem has no initial data. This problem has no source term. So now if you have a heat equation problem that has a source term and initial data, add them together. So you'd have this featuring your initial data plus this featuring your source term. Because it's a linear PDE, so you can add solutions together like that. So, questions about this? Now, I'm not going to take the time to prove or derive Duhamel's principle here. However, what I can do is give you an explanation of why it holds by falling back on something much simpler to digest. That's ODEs. Okay. So, and I do not understand why in any book on PDEs, when they discuss Duhamel's principle, they never tie it back to ODEs. It's like, it's so obvious. And it's something that really helps students understand. I don't know. So this comes from this. A simple first order linear ODE. So you have that, and so Q is playing the role of your source term, and then you have your initial condition. So that has a solution. Yt is equal to e to the, well, actually, I'm gonna make this a little simpler. I'll make p of t a constant, so it's less cluttered. Okay. So e to the pt, y naught, plus integral 0 to t of e to the p t minus s q of s ds. It's the exact same thing. This is a solution of a homogeneous part if you were to ignore the source term. See, it involves the initial data. What's happening here? At each instant s, function q at that time is treated like initial data. It's evolved from time s to time t in the same way that the homogeneous solution is made. And all of those are integrated. That's just a superposition. That's this integral from 0 to t. So it's kind of weird because I remember learning about Duhamel's principle in whatever PDE class I was taking. And then I actually never took a first course in ODEs as an undergrad. They just let me through. I'm not sure why, but when I had to teach it some years later, not sure how they let me do that. And I'm doing this. It's like, this is Duhamel's principle. So I think it's important to link the two. Because a PDE can be decomposed into, a linear PDE can be decomposed into linear ODEs like this one, using like eigenvalues and eigenfunctions that you've all been exposed to from whichever PDEs class that you've had. Let's see. 517, 517, 517, 606, 606. So you, both classes would have dealt with that. So then, in that case, you really can express the solution of inhomogeneous PDE through this stripped down form of Duhamel's principle for ODEs. So that's my rant about how things are taught, because I don't understand why these connections are never explicitly made in class. Because I just think it helps, but.
They assume you already know that.
My rule of thumb for teaching that's solidified during my 12 years here at USM is that students will not remember anything, and it's best to just go about assumption. It just makes things easier. But it's also like riding a bicycle. Like, you remind them, and it starts to come back, so they can still work with it. But as far as like actually remembering off the top of their head, like, no, that doesn't happen until you teach these things. And then you can't forget even if you want to. But until you get to that point, like, okay. Any questions about this? I know I got a little ranty during that stretch, but it'll happen again. So.
It's okay, we've come to expect that at this point.
Oh yeah. All right, so I prevent myself from getting bored. Okay. All right, now, so I want to mention some properties. Okay, so now, look at the equation on a bounded domain. Okay, so this is a Ibvp, initial boundary value problem. So same PDE. Okay. Let's see. So X is in some domain omega, and T is in interval 0 to capital T. Then we have initial data. And then we have boundary conditions. So U is equal to G on the boundary of omega, and still the same interval in T. All right, so we have an initial condition at time 0. We do not have an end condition at time capital T. It's not necessary for well-posedness. Okay, so we have this. So the heat equation has properties similar to solutions of Laplace's equation. So first we have a maximum principle. That's pretty much exactly like one for Laplace's equation. So the maximum of U in the interior, the maximum is equal to is assumed on the boundary. Okay. Go 0 T. Okay. I need to define the space-time boundary. Okay, where omega sub capital T is defined to be omega Cartesian product with a closed interval 0 to capital T. So maximum of U on the entire region is assumed somewhere in the boundary of this region. So that could include either somewhere in omega at T equals 0, or it could be on the boundary of omega, but at some time in the interior. So the boundary of this region in some sense, or a boundary in space or a boundary in time. Somewhere in that boundary is where the maximum has to be assumed. So same maximum principle in Laplace's equation. And that leads to uniqueness. So just like Laplace's equation, you can apply the maximum principle to minus U to get a minimum principle. So then if you have two solutions of the same initial data and same boundary data, you take your difference at 0 on the boundary in space and time. Therefore, the solution must be 0 throughout the region. So all that works the same as in Laplace's equation. Okay. Let's see. Something else here. Oh, actually, yeah, that's all I got, one property. Okay. Now, what I've written here is the weak maximum principle, saying that the maximum is assumed on the boundary. For a Laplace equation, I have to state a strong maximum principle. And for Laplace's equation, that's stated that if the domain is connected, then the maximum cannot be assumed in the interior unless the solution is constant. That holds here as well. So now the domain in T is already connected, but I haven't stated that the spatial domain omega is connected. So you have a weak maximum principle regardless. But if omega is connected, you also have a strong maximum principle. All right, so I'm not going to go through details here just because the details work exactly the same way as in Laplace's equation. Okay. One thing to be careful about notation-wise. the boundary of omega, as we work careful how I define that. When I say the boundary of omega t, I'm not including the top part at little t equals capital T. So the maximum would not occur there. It can occur at little t equals 0 though. It's a very strange way to define boundary. It's not technically correct, but as long as I make a qualification, I just want to be able to use this boundary notation just for conciseness. So I guess there really is no non-cumbersome way to express this. Right, so questions about any of this? Okay. All right. A little early, but this is too natural a stopping point. I'm at the end of this section, I'm about to start another section, so I'll just do a 5-minute break here. And I'll get some better chalk.
There's a whole box of chalk in my office on the second floor. I'm not sure if it's the right kind, but you can have it.
Oh, well, I still play in my office, but I'll keep that in mind.
It's okay, I bought an $1,100 graphics card.
I bought $300 for plushies, because I am a little child.
How much?
300?
I thought it was one also 1,100.
Just to be fair,
I did buy a $3,600 motorcycle.
Put that get you around, you know.
Well, it's not for me.
and to be fair, that graphics card, the MSRP on a 3070 Ti is supposed to be like 700, but the market is shit right now. As in the graphics card I have in my computer right now, I bought about 4 years ago for $200.
Yeah.
That is about a 5-year-old card that was $200 when it first came out. That graphics card right now on eBay and stuff is selling for between $300 and $400.
You should sell it on eBay is what I'm hearing.
I-
Because if you sell it for $400, but then you bought a $700 graphics card.
No, I'm selling that RX 480 to a friend of mine for 150 because I do not agree with that pricing at all.
That's right.
Because again,
But you want to know what I bought?
what?
I bought Flareon, Victorion, and Jolteon plushies,
So,
and a Grover plushie.
so if you don't want the Evolution plushies, I'll take them off your hands.
I want them. I have notifications to get Umbreon and Espeon.
I'm doing stuff for Dr. D because I have my meeting with him here in a little bit. Why is this gotta be so complicated? So this is a nonlinear coupled system of ODEs,
Okay.
which would be okay except for this first time derivative, and here's a multiplication of the first time derivative of x1.
Yep.
I'm just like, I really don't know how to handle this.
Yep, sounds about right.
I don't even know what you just said, so.
Dr. Lee asked me, goes, how do you feel about topology? I was like, please, Dr. Lee, no.
Oh, yeah. He has me working on physics stuff right now, so.
That's fine. You enjoy your physics. Last time I took physics was as an undergrad, and it was physics 1.
I minored in physics as an undergrad, and I've taken a couple graduate level physics classes.
Yeah, I would be lost.
Yeah, he has me looking at harmonic motion on, right now he has me looking at harmonic motion on a hyperbolic plane.
Yes.
He made the comment he wants us to be done with this by the end of the semester.
Oh, isn't that lovely?
I'm just like,
He's very ambitious, sir. You pretend I'm that smart, Dr. Lee. And people are like, you're so smart. I'm like, I just don't agree with you.
he asked me if I was familiar with stochastic processes. I told him, I mean, I know the term, but I'm not super familiar. He's like, well, have you studied Brownian motion? I'm like, we touched on it for like one lecture in statistical mechanics, but that's it. Oh, okay, we may look at some Brownian motion.
I'm excited because guess what came in the mail? You probably got it too, Robert.
Sales papers.
Oh,
Really?
yes.
Well, on the website, they said they weren't supposed to start mailing them until the end of this month.
Nick said that my diploma is sitting at the house with me right now.
In that case, I really hope my mailman did not just shove it in my mailbox and get it. That was so.
I would be so pissed. I would cry. If you said you might have gotten your diploma too.
That's good. You got an email on that. I need to look at the international office.
Oh.
That's the international decided to set up an appointment, and I don't have time for it.
I'm sorry. Can we get someone to pretend to be you?
We know me.
Okay, so we'll have Chelsea teach your class so you can go.
I was about to say, I do not think I could take Samson's place. I do not look enough like him.
Well, these new gloves are not one of them good.
I thought Sarah was supposed to go. I'm happy to go back to not teaching on Thursdays.
It's all for yourself.
Well, something caught that wasn't supposed to.
So frustrating, like I get back to my office, get the damn mask off, do like 2 things on my phone, and then it's time to get back in here. Like, what the hell? It's always the fastest 5 minutes.
That's the worst when you're teaching the class and you try to have a break and then students ask you questions the whole break and you don't get a break.
That's why I run to my office. Yeah, because I used to do that. I would stick around, and then it's like, well, I don't really get a break now, do I?
I can't remember what it is, but my dad is coming out that like this.
Yes, you did.
I'm so excited.
That's very nice.
I know. I was like, are you allowed to do it? He goes, being allowed to do that and doing it are 2 different things. I was like, no wonder why my sister calls you a terrible role model.
Theme 2 was pretty fundamental PDEs, Laplace equation, and its close relative Poisson equation, and then the heat equation. So now I'll talk about the wave equation. But first, a simpler transport equation. Which models advection as opposed to a heat equation modeling diffusion. So this is for real propagating waves. So transport equation is also time dependent. So we have the inner product or dot product of this given vector b with the gradient. Okay. So, and here I'll just talk about the free space problem. Okay. And then we have some initial condition. Okay. Now, the solution is actually very easy to describe. So u of xt is u naught of x minus TB. Now, here I haven't always written the vector symbol for x, but x has been understood to be a point in Rn. It is an n-dimensional vector. But I'll put a vector symbol on it just to be consistent with the vector b here, which is a vector also in Rn. So, so just the initial data where we have a shift. So like we saw earlier in the one-dimensional case where we had a graph like shifting to the right, here we just have shifts in each dimension. Okay? And how much of a shift, how rapid a shift, depends on the components of B in like the X, Y, Z directions or whatever you have. And to verify the solution, you can use the multivariable chain rule. If I just go ahead and compute du dt, well, by the chain rule, that would be u naught or sorry, it would be the gradient of u naught. Okay. So it's like a chain rule, derivative of the outer function, that's what we have here, times the derivative of the inner function. But times in this case is dot product because the derivative here is a gradient, which is a vector. So now we have a dot product of the derivative of this with respect to time, but derivative of this with respect to time is just minus the vector b. But that's equal to minus b dot product with the gradient of u. That's right here. So ut plus b dot gradient of u is 0. Right. And certainly you can see that if we substitute t equals 0, we're just going to get the initial data. So that's all it takes to verify the solution. Questions about that? Now, just like I did with the heat equation, I can easily solve the corresponding inhomogeneous problem. So I have ut, same PDE, almost, but it's equal to a source term f, and then we still have initial data. Okay. So I can write that solution using Duhamel's principle. I see Dr. Cole has gotten a bit more talkative than earlier. So u of xt will, so a first term will deal with just the initial data. So that'll be, it'll be exactly that. So u naught of x minus tb plus, so the second term will deal with the source term. So what do? We take the source term, and at each instant s, so this will be an integral with respect to s from 0 to t. So f is a function of x and t. So we evaluate it at time s, and then we treat it as, so that's initial data, and then we evolve it from time s to time t. So what does that mean? It's the same thing that we see here, x minus, but because we're starting at time s and going to time t, this time span is t minus s instead of just t. Okay. Yes, even after all these years, I still feel that sense of relief where I'm writing at the board, not really paying attention to my notes, just working everything out in my head. And then it actually agrees with what's in my notes. Sometimes it doesn't. It's like, oh God, what did I do? Which one is wrong? And you never know. Sometimes it's a note, sometimes it's me at the board. So, okay. So that's Duhamel's principle in action. So starting at time s, propagating to time t. Okay. All right. So questions about that? So it's nice that the solution to this problem has such a simple form that allows us to express this solution in a similarly simple form. Okay. So now what I want to do is use this to solve the wave equation. All right, so what I want to do is leave this up here so that I can make use of it. All right. I'm not sure if I can get through all this in half an hour, but we'll see. I shouldn't have done that. Not yet, anyway. Well, at least, what's there? Well, really, the only thing I need to do with pictures is that there's something I wrote on the board that is not in the notes that I can put in there, but that I wrote there is in the notes. So I'm not heartbroken about it. Erased, but okay. Okay, so now the wave equation Pde that's second order in time. So that's UTT minus Laplacian of U equal to F. So the transport equation is first order in time and only first partial derivatives in space. But here we have second derivatives in space and time. Okay, so so now what I'll do is consider a homogeneous initial value problem. And I'm going to limit myself to one space dimension for simplicity. And I'll talk about 2D and 3D later. All right. So UTT minus UXX is 0 on the whole real line. And then we have our initial data. Now, because the PDE is second order in time, we need two initial conditions, one on U and one on DUDT. Okay. Now, what I'm going to do with this PDE is factor it. Because you can think of this, what's being done to U as a difference of squares. What's being squared? Differentiation operators. So you can think of UDT as you're taking the differentiation with respect to t, squaring that operator and taking derivative twice. And the same thing here with x. So UTT minus UXX is the same as derivative with respect to t squared applied to u minus derivative with respect to x squared applied to u. So really I can factor out u. So now I can factor this operator. So dt plus dx minus dx. that must be 0. So now what I'm going to do is I'm going to take this and I'll call it V. So now I'm back to a transport equation for V. So V is the solution of transport equation here with B equal to 1. Okay, so Vt plus BVx equals 0. B is equal to 1. So, because of what I showed you earlier for transport equation, I know how to solve that problem. So V of xt is equal to some function, which I'll call A, x minus bt, or x minus t, because b is 1. Now, I don't know what A is. If you look back to what we saw in the transport equation, the solution of transport equation expressed in terms of the initial data. But I haven't shown you initial condition here. So whatever the initial condition is function A of x. That's the solution in terms of it. We'll come to that later. Okay. Now, okay. I need to leave that there, so. I don't know where we're standing next to you to take these pictures. Right. Questions about that? Okay. So now what I need to do is okay. I have this involving V. So if I take the equation that defines V, now I need to solve that for you. So ut minus ux is equal to V. That's the equation that defined V in the first place. But that is equal to A of x minus t. Okay. Now, we recall that we have an initial condition for u, now be g of x. So now I'm going to use that. So here we have a transport equation with an initial condition and a source term. That's this problem right here. In this problem, b is equal to minus 1. So when I use this solution formula, I have to take that into account. Okay, so using that solution formula, I can say that u of xt is equal to the initial data, g of x plus t, because here we have x minus tb, but b is minus 1. Okay, this minus 1 comes from that coefficient of minus 1 there. Okay, plus, now we have the integral 0 to t So my source term is what goes in here, but I have to be careful now because so first argument is going to be, so this is what goes in place of x. So that's going to be a of x minus t minus s. And then b is minus 1, so I'll fill that in. But I also have this minus t, can't forget that. But that's going to be s, because I'm evaluating solution at time s, because of this right here. Okay. Okay, so question about where that came from. So the idea is, this is a spatial argument, this is the time argument. You fill them in for x and t in here, and this pops out. All right. If you're not sure about it now, I encourage you to look back later, like in the notes, but it takes time to really see everything. Now, this is, let's declutter this argument here. So really what we have is x minus a minus t, and then I have minus a minus s, and another minus s, so it's minus 2s. So that's the actual argument to A in that case. Okay. Now, this whole argument I'm going to call y. So I'm making a, I guess you can call it a y substitution. Okay. So then ds is equal to minus 1/2 dy. Also, if I substitute in s equal 0 or t, then the new limits will be x minus t and x plus t. So this becomes g of x plus t plus the integral plus 1/2 integral x minus t to x plus t a of y dy. So after implementing a whole y substitution, it condenses to that. So it's a lot nicer to work with. So we almost have a solution, but this function a is still unknown. So we have to make sure that this solution satisfies the initial conditions, both of them. Now if I substitute t equals 0, I get g of x from here. And this integral will become 0 because the integral from x to x. So it does satisfy that initial condition. So I have to make sure that if I take the derivative of this whole thing with respect to time and substitute t equals 0, that I get the other initial data. That's h of x. Okay. So h of x must be equal to whatever I get from here, differentiate with respect to t, and then substitute t equals 0. So for a first term, that's just going to be g prime of x plus t, but then t is 0, so that's g prime of x. Then for the other part, I'm going to take a derivative of this integral with respect to t. So that's going to be, by a fundamental theorem of calculus, a of x plus t times the derivative of the upper limit with respect to t, which is 1. And then minus a of x minus t times the derivative of the lower limit with respect to t, which is minus 1, all evaluated at t equals 0. The minus and the minus gives me a plus. So I get g prime plus a of x. So now I know what a is. A is just h minus g prime. So now I can substitute that in here. So u of xt is g of xt equals 1/2 integral. So a is equal to h of y minus a minus g prime of y dy. Oh, sorry, that's x plus t. Now, here I have an integral of a derivative. So I can evaluate that. So now I'm going to have minus g of y with limits of 1/2. X minus t and x plus t. And then the rest of the integral I'll just leave as is. So then when I plug in the limits and simplify as much as I can, this is what I get. And we're done. So that's a solution in one dimension. Does anyone remember from either of the other PDE classes what the solution is called?
D'Alembert solution.
Yes, D'Alembert solution. Okay. Okay. So questions about any of that? All right, now that's just one dimension. So what about higher dimensions? Well, before I do that, what we see here is the initial data, half of it is shifted to the left with speed 1. The other half shifted to the right, also speed 1. The initial velocity is accounted for here. So just how it behaves. So suppose the initial data is mostly 0, except in a small subdomain. Then the solution will be 0 most of the time, except for these propagating half blobs that go in opposite directions, especially if this part is 0. But we get different behavior depending on how many spatial dimensions we're in. Now you might think that since I just talked about 1D, that next I'll do 2D and 3D, but I'm actually going to go in the opposite direction. So 3D, we have UTT minus Laplacian, 0, so we'll have no source term in this case. Okay, so that's our initial conditions. So the solution is given by Kirchhoff's formula. Okay. So it's defined as an integral over the boundary of a ball centered at x, radius t. And what we're integrating is t times the initial velocity at y plus the initial displacement at y, and then we have an additional term, gradient g dot product with y minus x. All right. So we're integrating over a sphere. So just the boundary, not the ball inside. So this leads to interesting behavior. That what we have is, suppose the initial data is 0 almost everywhere, except say maybe it's a delta function. But the solution, as time marches forward, is 0 mostly everywhere, until t gets sufficiently large, and it gets something non-zero at a given point x. Like if you're watching what happens at a specific point x, you have this wavefront that's passing through x, so the solution is briefly non-zero. The wave passes through, and then at the point you're observing, the solution becomes 0 again. So we have a sharp leading edge and a sharp trailing edge. So that's what happens in 3 dimensions, because you're integrating over the boundary of the sphere, not the inside. Okay. All right. Now, so what about 2D? Okay. Use what's called the method of descent. Where you assume that initial data has no dependence on z, it's a function of x and y. And you rewrite this integral that's over a 3-dimensional entity as one over a 2-dimensional entity by taking this sphere and flattening it. But that means that now in 2D you're integrating over the interior, over a disk rather than a sphere. So the behavior of the solution becomes very different. Now, I'm not going to go ahead. I'm not going to write the solution in this case. Just the main point is that the integral over b of xt rather than the boundary of b of xt. But here's a 2-dimensional ball. There's a 3-dimensional ball. And so then we don't have this sharp front anymore. So at a certain point where you're observing a solution, it's 0, 0, 0, eventually becomes non-zero. Once it becomes non-zero, it remains non-zero for all time after that. Because you're integrating over a ball, a disk that's growing larger and larger. It's always going to have something non-zero in it, once there's anything non-zero at all. These notes here do not have the details of how this formula or the 2D formula is derived, just the main idea. But all the gory details you can actually find in my 517 notes, where I actually did all the scary multivariable calculus, including the method of descent. And yeah, it was ugly. So, but here in this class, we're focused on numerical methods. But still, it's important to take some time to learn what is known about these solutions to these PDEs analytically, like a properties of solution, like the maximum principles, uniqueness, mean value property for Laplace's. Whatever solution has a sharp front in the wave equation or not, because if you know how the solution behaves analytically, then you want your numerical solution to exhibit that same behavior. You want it to be consistent with that. So, okay. Well, I managed to, well, owing to a little bit of laziness in terms of not running everything down, I'm caught up. That's one way to make it happen. So then on Tuesday, I will start with the numerical methods, finite difference methods, starting with the Poisson's equation. Questions about anything? Anyone, or including like if anyone's working on the first homework problem? Or?
I'll bring you questions when I actually start it.
Okay.
I'm like, I'm taking your hint, you keep asking for questions, but.
I know. It's just to fill time. So.
I promise one day I will start the homework. It just
Okay.
has not been today.
Yeah.
Okay, that's something. Thank you for that, I guess.
I have the first problem written down in my notebook, but I haven't started it.
Oh, okay.
So at one point I did finish it, but then I decided no.
All righty, well, let's shut this thing down then.